Hello, dear colleagues. I would like to present our report, Effect of Mineral Additives to a Gypsum Wet Deformation. Gypsum binder-based materials are characterized by ecological safety, sufficient strength and durability, and also by low weight and relatively low heat and sound conductivity. Due to these advantages, gypsum materials are widely used for construction purposes. However, their insufficient water resistance that result in an essential loss of strength in the case of their water saturation and or wetting restricts the field of their broad application. A low water resistance of gypsum materials is mainly explained by the calcium dehydrate solubility and the wedging forces that are created by the water that penetrates into the pores. As for today, many methods are available that can increase the gypsum water resistance, in a particular decrease in the water to gypsum ratio, an addition of polymer additives, impregnation and hydrophobization of the surfaces of gypsum stone, combination with hydraulic binders, addition of the active mineral additives and additives microfillers that contribute to the formation of the dense structure of gypsum stone. During the studies carried out to improve the compositions of gypsum binders, the water resistance was evaluated by the toughening factor, the compression strength ratio in the water saturated state and initial dry state. Hence, the studies of the volumetric strengths of artificial gypsum stone with mineral additives and their relation with the water resistance are an important task. A low water resistance of gypsum items is explained by the high solubility of gypsum dehydrate equal to 2.04 Ga. In addition, the water that penetrates into intercrystalline cavities is absorbed by hard surfaces, and the wedging pressure is created between them that disrupt local contacts between the crystals. The water resistance, the gypsum binders can be increased by a decrease in the water to gypsum ratio, by combination with hydraulic binders, and by the addition of mineral additive fillers, hydrophobization additives, polymers, and fiber. The structure and the properties of gypsum material can also control through the addition of mineral fillers and other binders, or a different composition and dispersion degree. The most stable composition of gypsum binders are gypsum cement pozzolana binders. Among the hydration products are not only calcium dehydrate surface crystals, but also low basic calcium hydrosilicates and other slightly soluble hydrates. They can form electroheterogeneous contacts with calcium dehydrate sulfate crystals that provide the formation of the water resistant structure. Based on the conception of the contribution made to low water resistance by the wedging effect of the water concentrated in the contacts between the individual crystals and particles in the structure, it was suggested to use a relative linear humidity strain caused by the water saturation, swelling, epsilon, as an additional indicator of water resistance. Research method to carry out our experimental investigation, we used the gypsum building plaster G10, ground granulated blast furnace slag Zaporizhstal, and the plasticizing additive sodium lingosulfonate in the amount of 2% of the gypsum mass. The ground granulated blast furnace slag Zaporizhstal had the following parameters that you can see on the picture. The humidity stain was defined using prism-like specimen with a size of 160/40 millimeters that were cured for at least 7 days and nights and dried in the temperature range of 18 to 22 and the relative humidity of 40 to 60% to get the constant weight. At least three specimens were used to test each composition. The specimen length L was measured in advance. Each specimen was inserted vertically into the container and the steel of glass plate laid over it. The indicator of clock type that was claimed in the laboratory holder was connected to it and initial indicator reading were recorded. The container was filled with the water to the level of the upper edge of specimen, and the indicator reading were taken every 0.25 to 0.5 hours during first 6 hours. A site was taken on it for at least 24 hours. The values of absolute linear humidity strain were measured for each time point according to the indicator readings. A relative humidity strain were measured for each time point. Based on epsilon values, the kinetic curve of the depends of epsilon on time was constructed, and using this curve, a maximum value of epsilon was defined, and the time required to attain it was recorded. The research data are given in next figures and table. Figures and table can show us that as soon as the specimens are immersed into the water, their length starts to elongate immediately due to humidity strain, the swelling. The strain was developed during 3 to 5 hours, and after that it attained a maximum value, and actually immediately it began to come down. It can be seen on picture 3 that the value of humidity strain depends on the content of the mineral additive, granulated milled blast furnace slag. A maximum strain is observed for the gypsum stone without mineral additive. A relative strain is decreased with an increase in the slag content. However, this decrease has no linear character. It was with by analogy to dependencies of the strain and water resistance on the slag content. It can be seen on next picture that minimum humidity strains are observed for artificial gypsum stone with relative slag content as G plus S 0.05 to 0.1 and above 0.27. It agrees with the character of dependencies constructed for the water resistance of the artificial gypsum stone as a function of relative slag content, and it confirms our assumption that the wedging effect of water concentrated in the contact between individual crystals and particles in the structure contributes to a low water resistance of gypsum. Hence, it's reasonable to use the values of humidity strains of artificial gypsum stone as additional indicators of its water resistance. Therefore, the supplemental addition of the granulated blast furnace slag to gypsum with the mineral additives result is no increase in the strength of artificial gypsum stone, and it can even condition a certain reduction of it. However, its strength is increased in the water-saturated state, and it results in an essential increase in the water resistance. The softening factor increased in the range of 0.6 to 0.8, and it can attain 1. The information given above confirms the theoretical conception that the addition of mineral additives to gypsum result in an increased amount of electroheterogeneous contacts in the artificial stone structure due to the fact that the pores are filled by additive particles. the experimental investigation shows that as soon as specimens are immersed into the water, their length starts to elongate due to humidity strain, in particular the swelling. The strain was developed during 3 to 5 hours, and after that it attained a maximum volume, and actually immediately it began to come down. It was established that the volume of humidity strain depends on the content of the mineral additive, granulated milled blast furnace slag. A maximum strain is observed for the gypsum stone without mineral additive. A relative strain is decreased with the increase in the slag content. However, this decrease has no linear character. It wave-like to analogy to the dependencies of the strange and water resistance on the slag content. Minimum humidity strains are observed for the artificial gypsum stone with a relative slag content of the G plus S 0.05 to 0.1 and above 0.27. It confirms our assumptions that the wedging effect of water concentrated in the contacts between the individual crystals and the particles in its structure promotes a low water resistance of gypsum. Hence, it's reasonable to use the various humidity stains of artificial gypsum stone as additional indicators of its water resistance. Thank you for attention.